Hello, everyone. Welcome to Chapter 6. We're going to continue our discussion about variables and look at how we can use certain tools to judge how strong the relationship is between two variables in healthcare. So let's get started and we'll have a look. And again, this is the chapter where we'll analyze the relationship between two variables. And again, this is really important in healthcare analytics because as so much of what we do involves asking whether things are related, like length of stay and charges, kind of an obvious one, or severity and resource use. As we go through this chapter, remember the goal is understanding the relationships, not to do the complicated math. These learning objectives will tell you exactly what you should be able to do by the end of this chapter. We'll look at how to assess relationships between categorical variables. Then we'll talk about sensitivity and specificity, which are two very important healthcare items to use with healthcare prediction. And then finally, we'll compare the two main types of correlation statistics that you'll see in practice. When we work with categorical variables, we often start with descriptive statistics, specifically contingency tables. These tables tell us how two categorical variables are related. So if we're looking at gender and discharge disposition descriptively, we can see differences in percentages. But the inferential statistics help us answer the bigger question. Are these differences meaningful, or could they just be due by, you know, odd chance? This is where chi-square test of independence comes in. The first step is always defining your hypothesis. The null hypothesis says that there's no relationship, that the variables are completely independent, excuse me. The alternative hypothesis says that there is a relationship. And so we chose an alpha level of 0.05. That's what it usually is. And then we identify the correct test statistic, which is this case is chi-squared. So again, this slide discusses how the expected cell frequencies are calculated. The important takeaway on this slide is not the calculation itself, but the idea that we're comparing observed values to expected values. If the differences are large enough, this suggests a meaningful relationship. So here is the chi-test statistic formula and the calculations. Again, we're not expecting you to memorize or calculate this by hand. However, we are expecting that you understand that this statistic summarizes how different the observed data is from what we would expect under the null hypothesis. Final steps are comparing the test statistic to a critical value and then deciding whether to reject the null hypothesis or not. In this example, the test statistic is smaller than the critical value, so we do not reject the null hypothesis. What this means is that we don't have enough evidence to say that there's a significant relationship between gender and discharge to home. Now we get into specificity and sensitivity. These are measures used to evaluate, oh, on the wrong slide, my bad. These are used to evaluate how well one categorical variable predicts another. And you see these a lot in healthcare when we're assessing screening tests or predictive indicators. Sensitivity focus on correctly identifying positives, while specificity focuses on correctly identifying the negatives. So here's a specificity, sensitivity, specificity example, excuse me. A health plan wishes to assess who is using their patient portal as a predictor of whether they will seek emergency care during the year. That is, they believe that patients who do not access the portal are more likely to have an emergency room visit. They collect the following data, and based on the enrollees, you can calculate the sensitivity and the specificity for a predictor of ER use. And this is where the contingency tables come in. So again, here are the calculations. And now we're moving into the correlation. Correlation is measuring the strength and the direction of a linear relationship between two variables. Pearson's correlation is used for continuous variables, while Spearman's rho is used when the variables are ordinal or when assumptions for Pearson aren't met. Most importantly, correlation does not cause causation. It only tells us that the variables are associated. So now we're going to get into Pearson's correlation coefficient, and we get into that a bit in the study guide. So basically, Pearson's correlation coefficient ranges from -1 to +1. If it's a positive, that means that the variables increase together. If it's negative, as one increases, the other decreases. And again, a good example of positive one is length of stay and charges in a hospital setting. So as you stay more days, you will have higher charges. We also have negative correlations. And again, for those of you who've taken coding, you can probably relate to this. As you acquire more time coding, more practice at refining your craft, you require less time to code records in general. And again, positive correlation, this makes total sense. As you stay longer, the costs go higher in a hospital setting. And again, here it is again, the correlation coefficient example, dealing with charges and hospital stays. And now we're getting into Spearman's rho. Spearman's rho is used when we work with ordinal data or ranked values. Instead of using the actual values, we rank the data first. This makes Spearman's rho especially useful in healthcare where severity levels or rankings are common. So I'm going to stop right there. And that's all I have for you. Come back, we'll finish our discussion about correlation and talk about some other topics related to comparing two variables. We'll see you online. Bye now.